Swayam Prabha, free DTH channel for education.
Hello everyone, welcome back to the online video lectures of the medical imaging course. In the last Zoom session, we started discussing about two-dimensional continuous time Fourier transform. In this lecture, what we are going to do is we'll quickly recap some of the key points about 2D continuous time Fourier transform, and from then onwards we'll continue our discussion about 2D Fourier transforms with the help of some examples. Let me move on to the notebook mode to quickly revise some of the key concepts that we discussed in the previous Zoom session. Let us start our discussion by rewriting the two-dimensional Fourier transform expressions. F of xy, the two-dimensional function, has been expressed as kx varying from minus infinity to plus infinity, ky varying from minus infinity to plus infinity. Two-dimensional Fourier transform f of kx comma ky multiplied with the complex exponential e power j times 2 pi into k subscript x plus k subscript y times y, integration with respect to dkx and dky. So this is the two-dimensional Fourier transform of the given function. How can we write the expression for it? F of kx comma ky is equal to, in similar lines, your x is varying from minus infinity to plus infinity, y is varying from minus infinity to plus infinity. The spatial domain function f of xy multiplied with complex exponential of e power minus j times 2 pi of kx times x plus ky times y, integrated with respect to x and y. Let's take a look at the synthesis equation. You notice that this e power j times 2 pi times kx into x plus ky into y, if you expand that, you are in fact writing it as cosine of 2 pi times kx times x plus ky times y plus j times the same function sine of 2 pi times kx times x plus ky times y. You could notice that you are in fact varying the variables kx, ky as you are integrating over kx and ky here, and you could think of representing f of xy as a combination of sines and cosines with varying weights for each of them. The weights given by f of xy, the Fourier transform, and the frequencies of the cosines kx and ky varying from minus infinity to plus infinity. That's the basic idea here. You could in fact write it as the real part plus imaginary part as well. So anyway, the analysis of cosine and sine are very similar. So our basis functions here are two-dimensional sinusoidal functions, as this is going to be a key building block for our two-dimensional Fourier transform analysis. We did a bit more rigorous analysis of what it means kx into x plus ky into y. Assume that you have a function, let's say the function you want to represent itself is a some cosine function of xy. Since that's a function of x comma y, we will take constant values for, assume there are some constant values for these frequencies. So we, let's say, have considered a function k naught into x plus k1 into y to understand what is the behavior of this function. That's what we have done in detail in the last class. So what is it that we arrived there? This function is periodic, but It's not periodic in any direction, it's periodic in a particular direction. So let me take x comma y here. If you consider the value at which this is maximum, okay, and then looking at when it is repeating, if you do the analysis based on that, you would see that this function repeats at an angle of, let's say, theta. If this is theta, this is also going to be theta. So that repetition point we are taking, where repetition of its peak, that's we are taking. So that repetition, let's call that periodicity of it as L. To do that, what we have done is this k naught x plus k1 y, making it equal to some integer value n. That's what we have done in our analysis. So with that, we have figured out that, let's say, whichever is there here would from the beginning, okay, from x equal to 0, y equal to 0, that for that to get repeated here, the same thing, it will have a periodicity of L. And before computing that, we figured out that this would be equal to 1 by k naught, and this intercept on the y-axis for this line, this is this gives you a line. For example, take that equal to 1, that would give you the intercepts. From that you could compute the intercepts both on x and y-axis. So 1 by k naught and 1 by k1 you got. And if you express the periodicity of that, what we arrived at, the expression is k naught square plus k1 square under square root. And then the theta will be, of course, you could compute simply by looking at the angle here, and that's a very straightforward one, where it would be equal to k1 by k naught. This is what we have done in the previous class. Now we will look at more specific examples now. For example, you take f of x comma y being equal to the same one what I have written there, 2 pi into k naught times x plus k1 times y. So far what we did is we got an understanding of how that function would look like. Now what we'll try to do is compute what is the two-dimensional Fourier transform of this function. Please pause the video here, work it out, and then cross-check that with whatever I am going to do right now. So how is this solved? You could write your f of xy as summation of complex exponentials, which is e power j times 2 pi into k naught x plus k1 y plus e power minus j times 2 pi of k naught x plus k1 y. Now in the last class itself, we have done thoroughly what would be the Fourier transforms of one and any function that gets multiplied by complex exponential. So from that you could right away, let's write that out here. Anyway, this is equivalent to looking at multiplying it with 1. For 1 it is delta of kx comma ky, that's getting multiplied by this complex exponential would give you the value of an impulse function which is there at kx minus k naught and ky minus k1, isn't it? Plus here again this is equivalent to kx plus k naught comma ky plus k1. So what is going to happen in the Fourier domain here? Let's try to draw the magnitude spectrum of this, where you have on the x-axis kx, y-axis ky. Assume that your k naught and k1 are positive values for the time being and real, of course. Let's say this is k naught minus k naught, right? k1 minus k1. You have one impulse value at k naught and k1. So here you have an impulse multiplied by, of course, 1 by 2, and another one at minus k naught and minus k1 at this location. Of course, the value here will be scaled by 1 by 2, and that's how your magnitude spectrum of kx ky would look like. If you want to double check this result from reconstructing f of xy from this f of kx comma ky, you could see here this is having values at only 2 points, k naught k1 minus k naught minus k1, and then you substitute them here and you would realize that the imaginary parts would get cancelled out and you would end up in getting 2 times cos of it, and then of course this 1 by 2 whichever you have here, scale it appropriately to get cos of 2 pi times k naught into x plus k1 times y. Hope this is clear for you. I would show you now some examples in the PPT presentation. Don't worry about these parts for the time being. I just took slides from other presentations, and also from this, also in this another one is you map your u whichever you find here to kx and v to ky. As you have seen here, there are two impulses at k naught. This is k naught and this is k1. This is minus k naught minus k1. So there are two impulses. Now if I am going to increase my k naught and k1, suppose, what is it equivalent to? It's equivalent to increasing the frequency of my cosine wave, is it not? So if I am going to increase that, what is going to happen is, ignore about the orientation for the time being, we would come back a little later, but this is an increased frequency by just looking at, for example, this distance, right? This is your L here, whereas here your L is something like this, which is more here. So you also take a look at the expression that we have derived. Our L is equal to k naught square plus k1 square. So if you are increasing the k naught and k1, the L would reduce. The same observation you could make here. Now here you could also see from these two figures, these are the ones which you could yourself plot by varying k naught and k1 values. Let's say this is your x value here and y value here. You could do it yourself for a fixed values of k naught and kx. Now another thing is the orientation getting changed, you could observe here. So another thing that you could make a clear observation is the values that you get in the frequency spectrum would be of course in the direction of the orientation. You could see it is periodic in this orientation, isn't it? So similarly you have this frequency spectrum, the delta functions are in the same orientation. Now take a look at here, or assume that this is your y. That's better. You are just plotting, you could have plotted it in the other way also, but you could for the time being consider this as your y, this as your x. This point you could see here, now your orientation is in this direction. Now look at the kx ky here, frequency spectrum of this, you would see them also in this direction. And of course you would also see the orientation is exactly same. This is not coming out of the blues. You could clearly see how we are reconstructing the signal that we have just seen. Now you could correlate that with this, why the orientation is same here. Now let's take a comparison between this versus the next one here. What you could see here, the frequency is increasing, which means your k naught and k1 are increasing. So the same observation you should be able to do here. So these values whichever are here, now the moment I am going to the next image, they are moving away here. Okay, of course now again this orientation would be in the same orientation as this one. These are just few observations. I want you to try yourself, implement these things in MATLAB, play with them and get more clarity about how these waveforms are there, orientations are there, how it is getting represented in the frequency domain, what happens if you have a cosine on the spatial domain, how it gets represented in the frequency domain. Suppose if I have just a cosine on the frequency domain, what would be its equivalent in the spatial domain? So I leave the rest of the analysis for yourself, and then I'll take you through few more examples. One function that we have already discussed in the previous class is box function, where this is your x and this is your y. From minus 1 by 2 to 1 by 2 on x, and same thing here on plus minus 1 by 2 to plus 1 by 2 on y. These values, this is 1. That's what I have considered. The difference for that example and this is, instead of writing it as minus 1 by 2 to 1 by 2 in every x and y direction, in x direction now we consider here this is minus capital X naught by 2, let's say, and here to x naught by 2. In the y direction, y naught by 2, and this being minus y naught by 2. So simple scaling is what would happen to your sinc functions here. You could there, in the earlier case, when x naught and y naught are equal to 1, you would get sinc of kx into sinc of ky. Now you would have scaled sinc functions here. So I want you to work it out yourself and cross check your results. Again, pay attention. In our earlier convention, we will be considering here kx instead of u and ky instead of v. The magnitude spectrum of two sincs in x and y multiplied, this is how it would look like if you are using intensities to plot it. Another expression, as we already discussed, is you use a surface plot, and this is how it would look like. The second example that we considered earlier is e power minus of x square plus y square. This is what we have already worked out. So this you could also represent it as minus r square. This is a extended example for it, where you are introducing the variance also here. This is a proper Gaussian curve that you are considering here. So this is essentially a 2D Gaussian. Obviously the 2D Gaussian is symmetric radially, and this is the result you have in the spatial domain. And then when you are computing its Fourier transform, notice that you would still get a Gaussian curve. Now your variance is inversed here. So lower the variance here, you could notice here your variance would be increasing here. Since I have done derivation earlier for this function and just a scaling of that would give you this, I leave this part to you to derive that. So these are the two important points to make a note of. One is a Fourier transform of Gaussian is still a Gaussian, and as far as scaling in terms of the variance is concerned, there is an inverse scale relation here. And I'll move forward to another important function, which is a 2D circular disk function, which is defined as shown here. As long as the radius is less than a, you have a magnitude of 1 and otherwise 0. So as we discussed in the last Zoom session, a circularly symmetric function would, the Fourier transform of it also would be a circularly symmetric function. So this derivation you might skip it, or it is up to you. It's optional for you to work out, as it requires a bit of understanding of the Bessel functions also to be able to derive it. But at least make a note of the kind of result that we are getting here. Notice here what is the Fourier transform that you are getting for this circularly symmetric function. So this is referred to as a Bessel function. You could see of it as a 2D version of a sinc. In all the radial directions it has a same value, as you could notice, but the values of this is a kind of a generalization of the 1D sinc to 2D sinc. This is more appropriate generalization than the earlier multiplication of sinc of x with sinc of y. Another example, you have now a delta function. This is delta of x comma y, what you have here, and what you are, that's the function here, and you would be getting as 1. Now this is where you are considering pair of impulses, right, which are there at plus a and minus a. Then what you would be getting there is a cosine function. Now these are in the y direction, so your f of kx comma ky will have sinusoid in the y direction. So you look at any line here, cross section here, and this would be having sinusoidal variations in that direction. So with that, now let me illustrate the same behavior with the help of some examples. For instance, assume that this is your image that you would like to represent in the Fourier domain. So if you try to imagine how it is getting reflected in the Fourier domain, is again, as I said, your u and v here are kx and ky, okay, and of course you do the same thing here. Then this e power j, you write it as cos of it plus j sine of it. So look at it into real and imaginary part, just focus on one of them. And then here inside it, these are the cos of 2 pi times kx times x plus ky times y, and kx and ky you are varying. So this is essentially equivalent to, for example, if you are varying only the kx, right, this is the kind of waveform you have. So this you are eventually representing it as, this would give you the weights that you are giving to each of those particular kx and ky. So alpha times this waveform, let's say, plus beta times this waveform plus gamma this times this. So the horizontal, for example, you are reducing the frequency, that would give you this, and then having both kx and ky, you would get it with some orientation now. So it's a linear combination of all of these rotated and varying frequency images of two-dimensional sinusoid. So you could think of f of xy in this manner. What it means by here, frequencies, low frequencies and high frequencies, this again you would know even from the background you have in DSP, that it is the details that gets represented by high frequency information, and it is the content that gets represented by low frequency information. In other words, the specific details are the edges. In order to construct those transitions accurately, you require high frequency content in your image, and the main content would be there in the low frequency images. So similar observations you could do here. This is your image for which I have computed, let's say, f of kx comma ky. Here I am showing you the magnitude spectrum of it. Now you just retain the low frequency content here around the center, and you make the rest to 0. Okay, this is what you want to have as your frequency spectrum. Now if you take this magnitude spectrum and reconstruct your signal, you would be getting this. This is, so you are allowing low frequencies and you are making the high frequencies 0. So this is equivalent to applying a low pass filter. So this is what the kind of result you would be getting. Now let's do contrary of it. Now from here, let's retain only the high frequency content and make the low frequency content 0. So this is equivalent to the high pass filter, and you do take an inverse transform here. This would capture the information of edges. This is more equivalent to having more smoothing or blurring. Let's make few more observations from few other images. Assume that in your image you have certain periodicity here. You could see the texture of this brick is getting repeated over the entire image. And now if you look at the magnitude spectrum has peaks at spatial frequencies of repeated texture. So the fundamental frequency and higher order frequencies at all those points, right, you could observe the texture. Again, there are different periodicities. Even if you are looking in this direction, there is some periodicity here. Even in this direction, there is some periodicity here. So that's why you could see periodicities both in this direction here, repeat for higher order frequencies, and also in this direction also you are able to see the periodic effect. That's one observation, but how could you make use of that? This is one example where you could make use of it. This is a scanned image where you have taken the thumb impression on a sheet which has some grid like structure, as you could see here. So now for your forensic analysis purpose, you want to get rid of all these grid points. It's quite easy to do this in the Fourier domain, as this is periodic structure. In the magnitude spectrum, you will have very high values for these repeated grid structures for the same reason that we discussed in the previous slide. So all you have to do now is you compute two-dimensional Fourier transform of this image and take the magnitude spectrum of it, and on that, whichever are having high values, you would see in these high points with high values, you remove those peaks from your frequency spectrum. So you make them simply to 0. You look at the profile of it, any value in the magnitude spectrum above a particular threshold, you just make it to 0, and to that you compute the inverse Fourier transform. As a result, the periodic background is we are able to successfully remove that. Another application where you could use is, this is the image obtained from a lunar orbital image. Because of the rolling of the shutter, it is mentioned that you are getting this kind of periodic effect in the background. This is done as way back in 1966. You have limitations from the camera point of view, and that's why you had this. So what you would do now is, again from here you compute the Fourier transform and look at the magnitude spectrum of this Fourier transform. Again, you could notice here the periodicity is in this direction. So that's why you would see here in this y direction all these points even at higher harmonics. So now you remove all these peaks here, make them 0 just like we did in the previous example, and on the resulting image you compute the inverse Fourier transform, and this is the image you would be getting there. Now we'll have a quick look at some of the properties of this two-dimensional Fourier transform. Let's try to have some intuition about them. So the linearity property holds good here also for the two-dimensional Fourier transform. And this is another important property. I leave the derivation part as an exercise for you, as you already know how to do that for a 1D case. So you convert it into our notations, f of kx by a and ky by b. That's what you would be getting. The shift, we have already seen the shift, so this already we are aware of it. Now another very important property is, suppose you have f of xy and you have rotated it, what would happen to the Fourier transform of it? Had it been, for example, something varying in the y direction itself, where you have only ky, these points would have been like this. Now this is equivalent to rotating it in this direction by 45 degrees, right? So you would notice here this would also rotate your Fourier domain. Again, this derivation part I will not go into it, that part I leave it to you, but I would just emphasize here that if you are rotating the image in the spatial domain, the frequency spectrum also gets rotated by the same angle. I will move on now to the convolution theorem. You all have done it in 1D. Extension to 2D is straightforward, so we will not derive it right now. Right away we will go through the final result here. So if you want to convolve two functions in the time domain, it's equivalent to multiplying them in the frequency domain. So this proof I leave it again as an exercise for you. All I would do is, how could we exploit this property of convolution theorem, right? For example, I want to convolve a given image with a 2D Gaussian. This convolution is much expensive by orders than the multiplication. Assuming that your Fourier transform and inverse Fourier transform computation is not so expensive when compared to this convolution, assume that I want to convolve my f of xy with a Gaussian kernel, and I would like to arrive at this result. Instead of that, how I could make use of convolution theorem is, you compute the Fourier transform of this. Now you take the Fourier transform of it. So then you simply multiply it, the frequency spectrum. Now to this you compute the inverse Fourier transform. Then you are going to get a result which should be identical to what you would have been getting if you are doing a convolution of this with this particular Gaussian. Okay, so with that we'll stop here, and that's all for now. Thanks for watching. See you in the next video lecture. Take care. Bye.